Thank you all for coming today. It is a great honor to be able to speak to you in IEEE Census 2021. I am Daisuke Hasebe from Tokyo Institute of Technology. Then I will start my presentation. I'd like to talk about a new model to predict mass spectrum from odor impression. First, I will talk about the backgrounds. While olfactory information has a great effect on emotion, it is not processed by computers. Although perfumer can create a scent, an automatic scent creation has never been tried. So far, mappings from sensing space onto odor impression space have been successfully made. Since the prediction accuracy has been recently improved, we can try to solve the inverse mapping. Our purpose is to make a mapping from odor impression space to sensing space. Because we have a technique to make a recipe of odor mixture from a sensing data, it makes sense to predict sensing space. The method is inverse problem, utilizing the previous mapping from sensing information to odor impression. Then let's talk about datasets. As an odor impression dataset, Dream dataset or SD data was partly used. In the dataset, 21 odor descriptors such as green, sweet, and spice were evaluated using 0 to 100 real numbers. For example, in this image, the score of green is about 10. As sensing datasets, mass spectra from NIST or MS data were used. This is an example of mass spectrum about trans-2-hexenol. And to train the main part of odor predictive model, common 383 molecules were included in SD dataset and MS dataset. And to train an MS autoencoder, mass spectra of 2335 molecules were used. In this section, I will introduce the previous mapping from sensing space to odor impression space. In this study, we used two autoencoders to extract features of SD and MS data. Autoencoder is a neural network that extracts features from its input to the middle layer. Also, it has a function to reconstruct the original input from the extracted feature to the last layer. So it has a symmetric structure. And in this study, they are trained by cross-validation. As for MS autoencoder, it is trained with 2335 molecules and then features of common 383 molecules encoded. As for SD autoencoder, feature of odor impression about the same 383 molecules are extracted. These extracted features are used to train a feature converter. In this slide, feature converter is introduced. First, MS feature is extracted with MS autoencoder. And this middle layer is the output of this stage. Along the dashed line, the MS feature is then mapped onto SD feature. Also along the dashed line, the output of feature converter is finally reconstructed with SD autoencoder. In this study, MS feature is to be explored. mass spectrum corresponding to the MS feature is reconstructed here after exploration. This is the image of the entire predictive model, and these are the number of nodes after optimization. About the prediction accuracy of the DNN, the correlation coefficient between predicted and target SD data was 0.918. This good mapping was used in the inverse problem. In this section, I will introduce how MS feature is explored with gradient descent method. Here is the MS feature search algorithm. The input of the system is target odor impression, and the output is MS feature to be predicted. First, MS feature is calculated with a trained MS autoencoder. And second, corresponding odor impression is mapped with DNN. And then, target odor impression is determined. And these three steps are for the preparation of the search. And fourth, the gradient of DNN is calculated here. Fifth, MS feature is updated according to the gradient. And sixth, odor impression is calculated again corresponding to the updated MS feature. And these steps are repeated 1,000 times. And finally, after iteration, MS feature with minimal SD error is chosen as the output. After all, the final output is calculated inversely against the previous DNN via the gradient descent. These are experimental results about odor impression. Here, I present a case where the impression of odor descriptor edible was changed. The left figure shows the result of a trained DNN. The horizontal axis is the target odor impression, and the vertical axis is the corresponding predicted odor impression. This means the left figure shows the good accuracy of the trained DNN. In the right figure, the target value of edible was multiplied with 0.6. Then gradient descent was applied. As a result, the intended impression of edible represented by red point was achieved because those plots are around the diagonal line in the figure. On the other hand, the other plots have decreased evaluation. This is possibly because DNN learned some correlation among odor descriptors. This is an experimental result about MS feature space. In the right figure, the circle plots are those just after encoded from the original mass spectra. The triangle plots are those after application of the gradient descent to the original SE data. And the square plots are those after application of the gradient descent to the SE data with the score of descriptor edible multiplied with 0.6. In any case, the gradient descent was done to minimize the difference between the target scores and predicted ones. And trained DNN can have some prediction error. Therefore, if R equals much smaller than 1, the gradient descent method can work to minimize the original prediction error of the DNN model rather than to achieve an intended odor impression. We call this model error problem. In the case of triangle plots, as the triangle plots were close to the corresponding circle plots, the influence of model error problem was not significant. And in the case of square plots, the square plots and the circle plots were not distant, even if the intended impression was obtained. This means the converged mass spectrum could realize the target odor impression while the original quality of smell was mostly kept. Conclusion. The purpose was to make a mapping from odor impression space to sensing space. As I introduced, we can make an odor prediction mapping from mass spectrum with good accuracy. So we use the mapping inversely to achieve our purpose, partly. As a result of the application of the gradient descent, intended odor impression of an odor descriptor was achieved, and odor impression of the other descriptor was changed under the influence of trained DNA. Small prediction error of the well-trained DNA did not change the result of MS feature exploration so much. MS feature exploration might not lose information about original smell. For future work, combination of mass spectra is considered to process odor mixture. Also, to validate the effect of MS feature exploration, real odor mixture will be made. This is the end of my presentation. Thank you for your attention.